Okay, so I think the recording has started. So thanks for joining us, everyone. Today we're pleased to have Rachel Oberman from Intel here. And she is an AI technical consulting engineer with Intel. Her background is in geospatial analysis and data science. Her goal is to enable customers to best optimize their workflow with data analytics and machine learning algorithms from Intel. And she has her degree in computer science and data science from the College of William and Mary. All yours, Rachel.
All right.
Oh, the format. I should have mentioned the format.
Yeah, sure.
Sorry. So there's a bunch of sections broken up here today. So folks want to put their questions in chat. Given the number of participants that we have, we'll sort of rein them in at the end of each section, roughly. Sorry about that. Go ahead, Rachel.
No problem. All right. Hello, everyone. As you got from that intro, my name is Rachel Oberman. I'm an AI technical consulting engineer with Intel Corporation. What that means essentially is that I help enable customers with the optimizations that Intel makes for machine learning frameworks and algorithms. And in turn, I also ensure that the customer voice is heard by the engineers and ensuring that the engineers make changes that best suit the customer. Throughout this presentation, we'll be going over a lot. So if at any point you think I'm going too fast, you cannot see the screen, you cannot hear me properly, and so on, please say so in the chat, and I'll take it upon the moderators to interrupt me and tell me to slow down, zoom in more, etc. Beyond that, we have, because this is a 2-hour workshop, we'll be going over a lot of topics. During the, as you can see, I've sectioned out these topics into different sections. At the end of each section, I'll call for questions that you could then ask in the chat. If I don't read them or answer them verbally or like notice them, I will expect the moderators to tell me I've missed a question. At the end, there's a couple of things that we can do. We could do a preview into deep learning framework optimizations. We could also do Q&A, more Q&A. There's a lot of Q&A that for the sake of time, I had to hold off on. We could do extra demos. Also during these breaks when people are asking questions, I'll be taking a moment to drink some water and stretch my legs. I definitely encourage you to do that as well. And without further ado, we'll begin with the agenda being that everything that I'll be covering today is part of the Intel OneAPI AI Analytics Toolkit. And I'll be talking about what OneAPI is and what the AI kit is in just a moment. Beyond that, we'll get into the components that the AI kit covers, including Intel distribution for Python and giving an overview of what's included in that. We'll be doing a little bit of a dive into Intel distribution of Modin, which allows you to distribute Pandas across multiple cores and multiple nodes. Beyond that, after that, we'll be going into Intel optimization for scikit-learn and XGBoost. And then we'll be taking everything together because in the past 3 sections, we'll be breaking up in by component of an end-to-end workload that a data scientist may cover. And we'll pull it all together and see exactly when you combine all of these optimizations, what kind of performance you can get. And then after that, I will do a few demos to actually demonstrate what this looks like in real time and what the actual changes look like. All right, with that, let's begin. So first, we're going to begin with discussing what OneAPI is. OneAPI is essentially, as you can see here, a cross-architectural language based on C++ and Cyclo standards. What that essentially means to you is basically, with OneAPI, Intel is trying to resolve the issues that many developers get in terms of having to install multiple things from multiple places, making sure all the dependencies are together, making sure everything is good for this CPU or this GPU. Rather than doing that, what Intel is trying to do is very simplify it and get it all in a single install. So with a single install from a OneAPI toolkit, there's different toolkits depending on the target audience and in terms of what each toolkit actually holds. Basically in a single install, you get everything you need and you'll get everything that will be supported by the Intel architecture. Currently, with the AI kit, we have CPU support. However, the idea in the long term that we are working towards is having XPU support, which means beyond CPUs, being able to have a single install that allows you to control these frameworks, these well-loved frameworks and development tools across different architectures without having to do all of this heavy lifting to ensure there's dependencies are like together, that memory is being allocated properly and so on. Today, we'll be talking about the AI Analytics Toolkit, which is part of OneAPI. Let me see if I can get to the next slide. There we go. OneAPI, the OneAPI AI Analytics Toolkit is one of the many toolkits that Intel provides as part of OneAPI. This one is targeted towards data scientists and data analytics and machine learning developers. And basically, within this toolkit, you'll find a bunch of well-loved frameworks and well-loved tools by data scientists, machine learning developers, and data analytics developers. And basically, we're compacting all of the Intel optimizations for these tools in a single place with actually pre-existing environments. So actually, when you install in that single install with the AI kit, you already get 3 pre-existing conda environments that you could activate into, one for TensorFlow, one for PyTorch, and one for classical ML. And as you can see on the right, this is everything you could expect as part of your Intel OneAPI AI Toolkit install. You get optimizations for deep learning with TensorFlow and PyTorch. You get optimizations for scikit-learn and XGBoost. You get optimizations for Modin. You get optimizations to core Python packages such as NumPy, SciPy, and Numba. And I'll be going over everything except the deep learning part as part of this workshop. And if there is time allocated, I'll give a brief preview to the deep learning aspect of this chart. If there is something, if there is something you're missing or something you want to dive deeper into that isn't part of this webinar, we have a lot of resources available, and a lot of them will be linked within this presentation that you should be able to get as a participant. And you could also learn more at intel.com/OneAPI-AI kit or software.intel.com/OneAPI/AI kit. I'll show you later, don't worry. Here is a better breakdown in terms of what the OneAPI as a whole covers in its different toolkits. Not just the AI kit, but broadly, if the AI kit is not for you, but you want something beyond TensorFlow, PyTorch, you want to deploy your deep learning models, you could get that from the OpenVINO toolkit. The OneAPI-based toolkit allows you to work directly with a lot of the libraries that actually bring you the optimizations that are in the AI kit. But with the AI kit, which is everything over here in the top left, is essentially abstracts out all of these optimizations given to you by these lower level libraries and allows you to make these optimizations with low to no code changes. I know that's a lot to cover, but as we saw with the AI kit slide here and here, everything that's part of the AI kit you consider in green here, TensorFlow and PyTorch, end-to-end workloads, the LPOT tool, low precision optimization tool, and then Maozoo for Intel architecture. Everything else, if there's something beyond that that you want to actually work with these optimization, with these libraries directly or deploy your models with OpenVINO, I definitely encourage you to look at those toolkits. However, once again, as part of the AI software provided by Intel, we're only covering AI kit today. I'm not going to go over this slide in detail. This is more so for reference. I know it's a lot of text, don't worry. I'm not going to read this out line by line, but essentially this is kind of going over the key features and benefits as part of the AI kit. So we have optimized like pre-trained deep learning frameworks as part of Maozoo. We have a lot of accelerations end-to-end, not only in classical ML, but also in deep learning that you're able to do in with drop-in replacements as part of OneAPI. You could support cross-architecture development. You could accelerate scikit-learn, XGBoost, and so on. Definitely encourage you to go back and look over this slide at the end. We've also shown this slide in different webinars. So if it's not this webinar, you could definitely see this slide in other places. But I'll be going over some of the stuff in this slide today in detail. Other parts I definitely encourage you to look at. And if you want to get started with the OneAPI AI Kit, we may revisit this slide at the end. Again, everything I'm covering today is part of the AI Analytics Toolkit. Again, in that single install, you'll get everything I'm covering today. And if you want a place to get started, like where do I get started after I install this? We have code samples available. We have documentation available. If you don't even want to install to your computer, you could actually go to Intel Dev Cloud, which is a great tool and platform that you can use that already has the AI Kit installed, and you could just sign up and play with the AI Kit that way. We have a lot of blogs that you should learn on the different optimizations and so on. And we have community forums where if there's something that I can't answer today, you could go there and we have speedy responses to those forums for your questions. Now that we've gone over an overview of AI Kit and how it's going to house all the optimizations that I'm talking about today, I'll next go into overview for Intel distribution for Python and its optimizations for NumPy, SciPy, and the other optimizations are included as part of this suite. Are there any questions at this time over OneAPI or AI Kit, or how to get those?
Haven't seen any show up in the chat so far.
Okay, I'm staring at the chat. Okay, awesome. All right, awesome. So with that, then I'm going to just keep continuing go over. Again, as I mentioned in the beginning, we'll be taking these breaks throughout as I transition from different sections, just so that everybody could take a mental breather on all the technical jargon that I will be saying today. So with that, let's dive deeper into Intel distribution for Python, which is once again part of the AI Analytics Toolkit. So the Intel distribution for Python is targeted at machine learning developers and data scientists, particularly in the classical ML space. You can consider Intel distribution for Python as a package suite within the software suite of AI Kit specialized for classical ML. With IDP, a lot of the optimizations for NumPy, SciPy, Numba, scikit-learn, and so on are actually powered by 1MKL library that I'll be talking about in just a moment. But essentially what the 1MKL library does is that under the hood of these packages, we go in, say with NumPy, and we take some of the memory intensive computations for NumPy and SciPy that usually like stock or standard non-optimized NumPy can't handle, and we plug in 1MKL, and basically 1MKL ensures that NumPy is doing the most to bring performance to your Intel architecture. Included as part of Intel distribution for Python are approximately 100 packages. A lot of them are dependencies, but the main ones that you're probably familiar with are NumPy, SciPy, and Numba, scikit-learn, and XGBoost, which are part of IDP and AI Kit, but I'm going to talk about them separately since they're such huge packages. Dolphy, which is another package that helps power our scikit-learn optimizations and can be used separately for even more power. And then our data frame packages such as Pandas and SBC. Modin is part of AI Kit, and although it's seen here in this image, it's highlighted in purple because it's part of AI Kit, and it is part of AI Kit, but it's not actually part of IDP, which you could also install separately. So just ignore that for now. We'll go into a deep dive of what Modin is with AI Kit in just a moment. And then you'll also get runtime libraries such as OpenCL and DPC++. So here's a better breakdown of what you get when you use Intel distribution for Python as a developer. In that single install with AI Kit, you get IDP. What does that mean when you actually use it? for things like such as NumPy and SciPy that you get as part of Intel distribution for Python, because it's installed by Intel, you don't need to make any changes to your code, and you get accelerations for NumPy and SciPy through 1MKL. With scikit-learn, you get optimizations from 1MKL, but also the 1DAL library, which I'll be going into in just later on, which will explain kind of all the 1DAL optimizations that help power scikit-learn alongside 1MKL. You also get optimizations for XGBoost. And then beyond that, you also get access to DAL for Pi, which beyond just a scale upwards and increasing your performance in a lot of these packages, DAL for Pi actually allows you, in the case of like scikit-learn, to get even like more performance. So rather than having to run all your scikit-learn algorithms like linear regression and k-means on just a single node, what DAL for Pi actually allows you to do is run these well-loved machine learning algorithms on distributed mode or online processing mode, meaning that rather than running on a single node, you can run on multi-nodes. And it's all optimized with the latest Intel architectures. The greatest part about this is that it's drop-in replacement. A lot of these optimizations, simply because you installed AI Kit, there's little to no code changes required. DAL for Pi is an extra API that's very friendly and very similar to scikit-learn that I'll be talking about later on and actually doing a demo on. When I say it's friendly and you're thinking to yourself, oh, I don't want to learn a new framework, what are you doing? No, it's a baby step from scikit-learn, and you don't even need to use it to get the optimizations for scikit-learn if you want to use it directly, just if you want to use that distributed online streaming mode. A lot of this is also available. It all supports Python 3. You could get this through Conda and pip package managers. You could also get it through AI Kit as well, and Docker Hub. This side, as you can see here, if you just want to try out this section, which includes scikit-learn, XGBoost, NumPy, and SciPy, you can install IDP separately, and it supports Windows, Linux, and macOS operating systems, and it supports Python 3 for these. You could also install with Yum and apt. However, I definitely encourage you to use the AI Kit, where if you don't want to install just IDP and also get, where if you don't want to just install IDP and you want to also get TensorFlow and PyTorch optimizations, you could get all of that in the AI Kit. And let's see, beyond that, something I also wanted to touch on, I thought there would be a little pop-up here, is actually with NumPy and SciPy, some of the optimizations for 1MKL are actually upstreamed to the default Conda channel. So actually, if you actually Conda installed NumPy and you didn't even specify that I wanted it from the Intel channel, if you just did Conda install NumPy or Conda install SciPy, you're actually getting some of these optimizations already seen. If you want even more optimizations, you could get NumPy or SciPy from the Intel channel, or you could get it from the AI Kit and you'll get even more optimizations. And if you want to compare NumPy and SciPy, which again are upstream to the default Conda channel, if you want to compare that to what's like without these optimizations, you could compare it to a pip install of NumPy or SciPy. I'm hearing some background noise, so if you are not currently speaking or a moderator, please mute. Thank you. Now with this slide, going back to this, this is a better breakdown of what's actually happening under the hood. You're hearing me say all of these are drop-in replacements. All of these you could get through AI Kit, and a lot of them are minimal code changes. Well, what's actually happening under the hood? Let's take NumPy, for example. Within Python, you have a well-loved package such as NumPy mathematical library. And what we do is we get around the BLAS API bottleneck, which helps usually handle some of the NumPy operations and memory handling. And rather than doing that, we just plug in the 1MKL library, which you could actually work with directly in other parts of the 1API toolkit. But in this case, we abstract it out so that you only need to handle NumPy to use it to get these optimizations. And that's all working under the hood. Again, if you're not comfortable with going in and tweaking these like 1MKL library, don't worry, you don't need to do it. All you need to do is just install the Intel optimized NumPy, and you'll get this performance. And you could see similarly with SciPy. Now, if you want to get into, like I said before, and this is a better breakdown, if you just want to get Intel distribution for Python, which includes like NumPy, SciPy, XGBoost, scikit-learn, all that good stuff that you saw on that previous slide. If you just want to get that, that's it. Not Modin, not TensorFlow, not PyTorch. If you want to get that, you can install it just separately through cont install, yum app, like a Docker image we have. You could play with it on DevCloud as part of the AI kit. You can do so. It supports Linux, Windows, and OS systems. You could also install it as part of the AI kit if you want more power beyond that. Let me see here. So that's just a better overview. As you saw, I specified more particular on the NumPy and SciPy optimizations. That is because we'll be getting into Pandas next with Modin. And then after that, we'll be getting into classical ML, scikit-learn, and XGBoost later on. Now I'm going to pause and take a moment because I think I see some questions. So let me see here.
Yep, there was a question on installation.
Yeah, so let's read it. I already have Anaconda Python installed. So if I install this kit, then will all those libraries be installed on top of it, or do I have to remove all those libraries first before installing? Good question. So essentially, if you're using a single Conda environment, then yes, basically, to explain it frankly, Anaconda, when you have Python installed and then you're trying to install another Python on top of it, like with AI Kit, which comes with its own Python, then it's not gonna like that. Essentially, with Conda, when everything in a single environment wants to handle that original Python. So what I suggest doing is that you can use Anaconda for this. You could create a separate environment, an isolated environment to use the AI kit. And then that way you could actually keep all your libraries together, and you do something like I'm going to type in the chat right now, like a similar thing for an empty extra environment, like conda create -n AI kit -modin or AI kit. If you created a separate environment with this and then a couple other details, this would create an empty environment if you see in the chat right here. So if you create an empty environment and then install the AI kit and that after activating into that environment, then all the libraries will be in their isolated environment to not conflict. Let me know if that doesn't answer your question. Are there any other questions before moving on? I'm going to take a moment here.
Yeah, I think that was the only one. I think previous incarnations of the Intel Python distribution before one API also recommended the separate environment method for installing it.
Separate. So in practice, as I've found with experience, having separate environments for everything is really great, especially when you're like creating like a new environment and there's like a lot of installs, and say there's another version of Python that just came out and updated. It's hard to update your Python because then it may conflict with the already existing packages in that environment. So I find conda environments to be really nice and really isolated, and in order to isolate those problems and avoid them from happening. That's why when you install AI Kit, if you did like an offline or online install, you actually get 3 pre-existing environments installed with it. So like not from conda install, but if you offline install AI Kit, you get 3 conda environments included as part of it. And then of those 3 environments, you get 1 for IDP, and then you get 1 for TensorFlow, and then 1 for PyTorch workloads that you could switch in between, and then mix and match and create your own with. I see another question on, also I have a system with AMD CPU. Will it work there? I don't think it will. You'll see the amount of optimizations. I'm hesitant to say it will work there. I don't think so. This is for Intel architecture. If Jeff is on the line, he could clarify, but I don't think so. I don't think we validate on those. All right. With that, I'm really excited to get into the next section, which is Intel distribution of Modin. And I'm actually going to pause before that. This is going to be the last question, and then I'm going to move on. And then if there's questions at the end or at the next section, I'll move on. But I see, what about older versions of CPUs? For Intel CPUs, The AI kit will work. You could look at the system requirements for the AI kit on the AI kit website, and it'll give you a breakdown of like what's the bare minimum you need for your system in order to run it. So I definitely encourage you to look at that. Those resources you can find on the Intel AI Kit website, as well as I believe there's like a link to it within here. Okay, moving on, we're going to now talk about Intel distribution of Modin, which is really exciting. Essentially, with Intel distribution of Modin, what happens is that you simply change, not even add, change one line of your code, and you get infinite scalability with your Pandas data frames. Now, I know what you're thinking, like, what do you mean by that? Let's get into it. So here's a current data loading and ETL landscape. If you've worked with Pandas before, you probably have an understanding of this. After a certain data size, if you're a data scientist and you're loading in all this data, after a certain data size, you need to change your API to handle more data. Typically, Pandas, which is a well-loved framework, especially for organizing and pre-processing your data before putting it into an algorithm or simply trying to get some analysis out of it. Typically, after say like around like 100 megabytes of data, Pandas will not perform very well. You're probably waiting ages for that to happen. And no one likes to wait around for their read CSV to finish running. So typically what happens right now is that you simply changed your API to Spark, which is very easy to scale your data and use for much higher data sizes. However, it is difficult to use and set up. So we have this wall where you either have to sacrifice your data size for easier to use APIs, but it's like difficult to scale, or you have to use easy to scale API, but it's difficult for you to use. Enter Modin. No matter the scale, just use the same API and spend the time that would be used to change your workload's API and use it to improve your workload and analysis. So in a single line of code change, what you can do is rather than having to go through the overhaul of having to install Spark, make sure it's running properly, then make sure your data is running properly, then change your whole end-to-end workload to run with Spark because you have so much data. From 0 to over a terabyte of data, you could just use Pandas data frames. That's breaking that wall with this easy to use, easy to scale API. Now, it's not even a different API. Modin is simply the Pandas API, but available to distribute and take advantage of all of your cores and all of your nodes to be able to infinitely scale your Pandas data frames. It all works with Pandas API, and as you can see in this nice GIF here, all you need to do is, rather than importing Pandas as PD, once you have successfully installed Modin, all you do is import modin.pandas as PD, and then you don't even have to change the rest of your Pandas API at all. It will automatically use Pandas after that. As of 0.9 version of Modin, Modin supports 100% of Pandas API. And if you don't think so, or if you have an issue with that, I definitely encourage you to email me or post it on the forum, and we will fix that. But it should support everything. If you see an issue, we'll help you either on the forum or directly with me. Just email me with your use case, and I'll be able to discern what's going on. The greatest part is also it works well with the rest of the Python ecosystem, so you don't need to worry about it breaking with if you're using NumPy, XGBoost, and scikit-learn and other parts of your workload. Don't worry about that. Just use Pandas as normal. And in the back end, which is special to the AI kit version of Modin, Intel distribution of Modin is supported by OmniSci, which is a performance framework for end-to-end analytics that has been optimized for Intel hardware. OmniSci is actually another company that we have partnered with. They have their own geospatial analysis platform, and within that, with that platform, they actually have something called the OmniSci SQL or OmniSci DB library, which we actually plug into the back end of the AI kit version of Modin that brings even more speed up to your workloads. So this is how it works. Essentially, you don't have to specify how many cores your system has. When you make this line change, your Pandas data frames, which are typically running on one CPU or one core, it'll distribute the Panda data frames to all cores available. And you don't need to know how many cores your system has, and it will increase your Pandas workloads in terms of performance by a lot. And if you want to test it out yourself, you don't even have to have a big machine. This isn't only for HPC only. You could also use it on your laptop. So if you actually installed Modin right now on your laptop and then went in to try and test this out, and I'll be doing a demo later actually as well to show this, you'll see the huge speed up you get. So no more time, and no more wasting time waiting for read CSV to run. Take that time and use it somewhere else for a better and more productive method. So this sounds great, right? How does it actually work? So here is a layered API view in terms of the software stack, in terms of what's going on. Right now we're working on Pandas. These things you see to the right are coming soon. But essentially, if you take the Modin Pandas, here's everything that's running under the hood. So with the query compiler and data frame algebra APIs part of Modin, those are helping optimize the SQL operations that are typically used with Pandas. Underneath that, we actually have Dask and Ray running underneath to do the heavy lifting of distributing your cores. Dask and Ray have their own APIs that are a little bit difficult to use, but this way you get to keep using your Pandas API and get that heavy lifting of distribution from Dask and Ray underneath, depending on what your system needs. If your system needs Dask, you use Dask. If your system needs Ray, you could use Ray. And then in this middle layer is actually where OmniSci comes in. So OmniSci comes in the backend processing, as well as like the query compiler, in terms of what we've done to enhance it in the AI kit version of Modin, which is also known as Intel distribution of Modin. So what does this performance look like? Here we take the NYC taxi workload, which is a benchmark workload of essentially a bunch of taxi trips between, I believe, 2009 and 2015, in terms of location, all this information about different taxi trips that happened in New York City. So if we look at 20 million rows, and we compare stock, or I use stock a lot if you've noticed. I consider stock as non-optimized standard Pandas. If we take that compared to the Intel distribution of Modin, which includes Modin and OmniSci, you could see a huge speed up on reading 20 million rows of this NYC taxi data set. So these Q1, Q2, Q3, Q4, those are different queries that we executed. And you can see here reading the CSV took around a little bit under 10 times the speed up. And then we have upwards of at least I'd say that's 17 times, depending on the query. But no matter what, Modin and OmniSci are running much faster than stock Pandas. Now, let's look beyond that. Modin has a lot of power that stock Pandas cannot usually handle. So we're going to actually increase the NYC taxi data set. So rather than reading in 20 million rows, let's read in 1 billion rows of that data set, which is 1.6 terabytes in memory. That's a lot of memory. So if we actually look at this, which is usually impossible for Pandas. So if you see here 0, it's because Pandas can't handle this. But Modin with the OmniSci backend can on 3 terabyte Optane. What that means in terms of speed up on 1 billion rows, which is an insane amount of data, you could get upwards of, in this case, you could see a 98 times speed up. And you could see here, that's around I'd say 10 here, 30 plus here, huge speed up, which is typically impossible. So not only are you getting faster than stock Pandas in terms of a regular use case, but again, that scale up, scale out, we're also scaling outwards and pushing the boundary in terms of how much data you can actually handle. Now I finished my portion on Modin. I'm going to actually hold on this slide so you guys could kind of think this in. And I'm planning on doing a demo on this later on. Let me actually go ahead and make sure everything stays set up for that. Are there any questions before I get into XGBoost and scikit-learn optimizations? Let's see, I have one. I have Intel i5 8th Gen. Do I need to have hyper-threading enabled? I assume this is in case for Modin. I don't think so. Again, it's just a single line change. You could also see the configurations lower below in terms of how these performance benchmarks, I believe these are also in the back of the slide deck that you'll be receiving. So you'll see the breakdown of how we actually measured these. And these are also available on the Intel website. Any other questions? Okay, I see one comment, but I don't see any other questions. So I'm actually going to continue on and into the optimizations for scikit-learn and XGBoost. So we touched on these previously, as these are part of Intel's distribution for Python, which is included as part of AI Kit. But now we're actually going to deep dive into what these optimizations actually look like. I'm going to first talk about Intel optimizations for scikit-learn, and then we're going to talk about the Intel optimizations for XGBoost and all the great optimizations and scale up performance you could get. Now, all of these optimizations are actually powered by the $1 library. You heard earlier that a lot of IDP is powered by 1MKL. And yes, scikit-learn and XGBoost do get a little bit, like a tiny bit of performance gain from 1MKL, but $1 is really the star in terms of what's running under the hood to bring you this performance. For these libraries, which work at every part of the end-to-end workload stack, especially for classical ML in terms of pre-processing, transformation, analysis, modeling, validation, decision-making, $1 helps bring you faster training and prediction and performance at every step of these workloads. And not only that, but we also give you a scale-out opportunity where you could use $for-pi to get even more speed up in your XGBoost prediction, or use distributed mode or online streaming mode for popular algorithms such as linear regression, k-means, and so on, if your ML algorithms really need it. So this is all powered by the $1 library, which is working underneath the hood to give you these optimizations. $1 is also available in C++ and Java APIs. $for-pi is considered the Python API, which essentially takes the C++ optimizations, abstracts them out to Python, then we abstract it further to scikit-learn. But you could use these APIs as well for C++ and Java. However, we find that Python is the most popular, especially with scikit-learn. So here is the better breakdown in terms of what's going on. I want you to ignore everything on the left and right, which are other parts of the end-to-end pipeline. We've already talked about NumPy and Pandas, so ignore that. But here is a better breakdown of what's running under the hood. In terms of what's going on, I definitely $1 is the star, and then 1MKL gives you some optimizations for some of the things that $1 doesn't typically handle, or 1MKL simply does better. So this is the breakdown for the optimizations for Intel optimizations for scikit-learn, Intel optimizations for XGBoost, and then $for-pi. Now, we just talked about how you get Intel optimizations for scikit-learn and how those are powered by $1. Now, I actually want to go in and get these optimizations and use them with scikit-learn. How do I do so? Typically, you would think that you simply you would have to change your scikit-learn install, or change that up. No, you could keep your regular scikit-learn install the same, And all you do is conda install or $PI, or you could get all of this in the AI kit or so on. You just simply conda install the $PI library, which is giving you all of these $1 powered optimizations through scikit-learn. So imagine I'm a user. I use scikit-learn. I have an end-to-end workload such as this that I want to use it for. I take that stock scikit-learn optimization. I just keep it. I don't change it. I install in the same environment $PI through the Intel channel. And then once $PI is installed, there's a couple of ways that you could turn on these optimizations for scikit-learn. The most popular way, which is what I encourage, is the two-step programmatic way, which is also known as the monkey patch. What you do is you simply import $PI as D for P, and then you use this function called D for P.patch underscore or sklearn. And what this does is it basically tells scikit-learn, hey, for anything that $PI and $1 optimize, turn on those optimizations. And anything that is optimized by $PI, those optimizations will be turned on. If those optimizations don't exist, like say for like a obscure algorithm that we haven't gotten to yet, then it'll just be stock scikit-learn. So there's literally no performance, poor performance or like performance drawback in terms of this. It's only performance gain. And then you just simply keep the rest of your code the same. You could import scikit-learn as normal after this. What this is doing is it's basically flipping a switch. That's basically telling $PI, hey, keep an eye out for anything like FCC, which is optimized, and optimize that. I want to note very clearly, this is all to basically extend and optimize. This is all essentially an extension, and it helps like optimize scikit-learn, but it's not scikit-learn-like. We're not looking to replace scikit-learn. It's all the same API. All we're doing is adding in 2 lines through $PI to bring these optimizations to life. And if you don't want to do this programmatically, that's okay. You could also do this in your command line by calling your scikit-learn script and then calling $PI with it, such as you could see here. You could also turn on an environment variable, and this is all detailed in the $PI documentation. And I'll be showing that later as well. Now, say that's not enough. Well, running linear regression batch processing mode is great. Even with the $PI optimizations, that's not enough. What can I do? No problem. You can use $PI, which makes those $1 powered optimizations in scikit-learn a reality. And you could use that $PI API directly. And what $PI has is that rather than just having the optimizations that you could get through the scikit-learn API directly, you could also use $PI directly in the API itself with distributed processing and online processing mode. And I'll actually be demonstrating the distributed processing mode and later on to actually show you what that means. But essentially, all it entails is you use the $PI API, which is again a baby step from scikit-learn. If you know how to use scikit-learn, it's not going to be a hard usage to use $PI. As you can see here with the k-means init, it has a very similar initialization methodology to scikit-learn. The only difference is that you're using $PI. And then if you wanted to use distributed processing or online processing, if your data is in chunks, all you have to do is turn on a flag in initiating these function calls and predictions. With distributed, you also have to turn on the distribution engine. So it's just 2 extra lines to turn on and off the engine. But that's all the processing modes that are available with $PI. Now, what is this optimization? What do these optimizations actually look like? What's the performance gain actually look like? Why should I care? Well, if you're tired of waiting for your machine learning algorithms to train or like run a prediction, no problem. We're going to speed up that time for you so that you could get further into analysis or tweaking your model again. So here's all the speed up you get by adding those 2 lines to your code. What we do with the scikit-learn optimizations that are powered by $1, we usually do it by popularity. So a lot of the most popular algorithms, such as like SVC, such as linear regression, such as random forest, all of those have already been optimized. And there's actually a list of the optimizations available on the $PI website. which gives you a list of everything that's currently optimized, and like if there's like certain like parameter like corner cases that maybe aren't optimized yet. But here's everything. We've even optimized a train test split, which gives you a 9.4 performance gain when you do that. But as you can see, with something like such as FBC predict, you can get over 221 times speed up with just two lines of code change, which is amazing. Now, how do we compare to our competitors? Well, here's a nice performance breakdown compared to AMD and NVIDIA with QML, and then running these optimizations on IDP. As you could see, across all of these function calls from scikit-learn, you could see that AMD and NVIDIA have a slower performance than the Intel optimizations for scikit-learn. There's also a blog discussing this, and as well as the configurations behind this that is available on Medium, as well as you can see the details here if you want to take a closer look. So it's pretty nice to see the speed up that we have. Now, if scikit-learn API optimizations aren't enough for you and you actually want to use DeltaPy, are you sacrificing any speed up? No, quite the opposite. DeltaPy is actually one of our most optimized ML libraries we have available at Intel. So if you actually went in and actually used distributed mode, as you can see with this hardcore scaling, as the number of cores that you specify increases, the execution time decreases on k-means fit, which is a huge, great thing to see. I'm going to actually pause here before getting into the XGBoost as like a slight pause. Are there any questions on the scikit-learn optimizations or DeltaPy? I'll be showing a demo later on these as well. Okay. If you don't have any questions right now on scikit-learn, you could also ask after the XGBoost portion of this presentation, and I will go through that. So we've talked a lot about the scikit-learn optimizations. Well, what about our XGBoost optimization? Fun fact, if you've actually pip installed XGBoost after, I believe it's 0.9 version, Intel actually upstream, Intel's optimizations for XGBoost are actually upstreamed to the pip installed or stock version of XGBoost. So what we're actually going to do is actually compare XGBoost before we began implementing these optimizations directly to before these optimizations directly to the most recent, as we've continued to provide these optimizations to the XGBoost code, and in terms of what these optimizations actually are doing. As I mentioned a little bit before, DeltaPy is one of our most optimized libraries. What we've done is in DeltaPy, we actually have a gradient boosting algorithm. But because we don't want to force our users to use DeltaPy to get that performance benefit, we actually take the logic behind what we do to optimize our gradient boosting algorithm, DeltaPy, and we take that logic and those concepts and apply it directly to the XGBoost code itself. And what those actually look like is essentially a bunch of memory optimization. So basically helping optimize like irregular memory access using better instruction sets. So like using uint8 instead of uint32, using parallelism where we can, and then taking advantage of compression, another good memory optimizations within the XGBoost code. And you can do this for, and this is for training and prediction. And here is the performance gain that we've done over time. So you can consider 0.81 the baseline, as we didn't do any optimizations to XGBoost there. But after 0.9, we began applying our optimizations to XGBoost directly. And just to pull out for a second before breaking down this benchmark, You could get XGBoost. You could get the optimizations for XGBoost through pip install XGBoost. That's also included as part of the AI kit. Again, I want to reiterate again, everything that I'm talking about today, you could get in a single install as part of AI Analytics Toolkit. Now, going back to the benchmark, let's compare the baseline 0.81 XGBoost on CPU to the more recent iterations of XGBoost, where we've applied our Intel optimizations. And as you can see here across well-popular data sets such as Higgs, letters, airline, these are basically large data sets that are popular for benchmarking. You can see a huge performance increase, especially over time as we've added more optimizations to XGBoost. This one is just on XGBoost fit, but I believe there's also similar optimizations to prediction. So as you can see, a huge performance gain for what in terms of the Higgs, you could see compared to the stock, a 15.5 times performance gain. So if you simply want to take advantage of these optimizations that I'm showing you, just download the or pip install the latest version of XGBoost from pip or use AI Kit. Now, how do these optimizations compare to one of our competitors, NVIDIA? As you can see, this is the speed up that you see on an Intel Xeon versus the NVIDIA V100. And as you can see here, there's at least a one-time speed up across these different well-loved data sets. With things such as Avalon, you can see a huge speed up, in this case, 4.53 times speed up. I believe there's also a blog on this. Yes, it's linked right here. So if you want more details on the configurations and the breakdown of this, I definitely encourage you to read that blog. Now, say you pip installed XGBoost, but you want even more performance, no problem. As I mentioned before, DolphinPy is one of our most optimized libraries, and we want our XGBoost users to take advantage of some of these optimizations without having to sacrifice the integrity of their XGBoost models or having to tweak and translate their model using a different API and then therefore changing the model entirely. No problem. What we've done with XGBoost and also with LightGBM prediction is that we've added a converter. So all you need to do is essentially in a couple of lines of code, and I can show this in a demo if we have time. I believe we will. Essentially, all you do is take your pre-trained XGBoost model. You've just finished training it. We're going to use XGBoost for this scenario. You've finished running XGBoost training on your model. You now have your model. After that, what you can do is put it into this function call, get GBT model from XGBoost. And what it will do is make the model without any tweaks on your end into something that DolphinPy can read. Now, after that, what you can do is then use DolphinPy gradient boosting classification predictions to, with your test data that you already have, and you'll be able to get a huge speed up by using DolphinPy gradient boosting prediction without sacrificing any of the accuracy or having to make any tweaks to your model. So you could see here in the performance benchmarks on the right that compared to just regular XGBoost, where again, we upstream some of these optimizations. If you wanted even more performance, you could see like at least like a 23 times performance gain as of 1.2 on the airline data set using the DolphinPy prediction. Again, this similar concept is also available for LightGBM. And as you can see here, there's no accuracy loss. I could also demonstrate this in a demo if there is time. But if the optimizations that we upstream to XGBoost isn't good enough, here's something extra that you can use without having to change your model or tweak it or abide by DolphinPy. Are there any questions on XGBoost or any lingering questions on scikit-learn before we take everything that we've discussed and put it all together? I'm going to give it a moment as I stand up, stretch my legs. And I also encourage you to stretch your legs as well. So I see a question on, but for training I assume this is for the XGBoost model, will the performance be the same as before? Yes, those $1 for pi optimizations you see here, that's only for XGBoost prediction, like GBM prediction. These will not affect anything with the training. We optimize, we upload a lot of optimizations to XGBoost fit or the training section. But this is only for prediction, and that won't impact anything. It won't slow down the performance of the training portion. Any other questions? All right, I got in a little good stretch there answering that question. So let's move on then. So we've talked about a lot of great optimizations that you could get as part of the AI Analytics Toolkit. We've talked about NumPy and SciPy optimizations for the Intel distribution for Python. We've talked about Intel distribution of Modin and how in a single line of code, you could get infinite scalability of your Pandas workloads. We've talked about scikit-learn optimizations. We've talked briefly about the $1 for pi distributed processing mode, as well as XGBoost optimizations that we upstream and a $1 for pi prediction that you could do to your XGBoost algorithm for further performance boost. What is it going to look like when we put all of these optimizations together? Let's take a scenario where you're a user, you've finished installing the AI kit, and you've made the tweaks necessary to optimize, say, like a census workload. So like predicting a person's education level based on income and so on. Here is the combined performance gain that you get with optimizations such as Modin and Intel optimizations for scikit-learn when you put them all together. So this is a census workload, which is once again a very popular workload that's used for benchmarking. And essentially this is taking data, as you can see here, from 1970 to 2010, and we're using a ridge regression-based training model to predict the education attainment level of a person based on income, age, and gender. So for read CSV and ETL, which is you could think of as like the dropping, transforming the data and loading the data, those kinds of things, those are all being handled by Intel distribution of Modin. Then for the train test split and then the ridge regression portion of this, we're actually using Intel optimizations for scikit-learn. And here is that performance gain compared to the unoptimized versions of that software stack. So for read CSV, you could see approximately an 8 times performance increase. For the ETL optimizations like drop NA, like organizing the data and so on, you could see, I believe that's like probably around like a 4 times performance increase. For train test split, simply splitting the data to get it prepped and ready for ridge regression, you could see around like a 8 times increase. And then for the ridge regression training and prediction, you could see almost a 60 times increase, which is huge, huge, huge. You're no longer waiting around for your model to train and predict. You could use that time elsewhere for an overall around like a 10 times faster end-to-end workload gain. Here is the breakdown on the left in terms of how long it took for each one moment. I'm running, just so you know, I have a second monitor where I'm making sure that the demos are ready right after this. So I'm just going, sometimes eyeing on the side to make sure everything's running properly. But for this phase-wise breakdown, you can see here that actually no longer is the breakdown, the majority of it is no longer happening in the ML section or even the ETL section. Actually, the majority of this breakdown is now in the train test split, which is a very interesting thing to see. Typically, it's usually in one of these other 3 sections, but with these performance gains, even with all this increase, it's mostly happening in train test split. So what did we do to our code to actually get this performance gain? Just this. All we did was add 1 line of code change to add this Intel distribution of Modin to our census workload. And all we did to get all of that performance gain and train, test, split, and then bridge regression is all we did is add in these two lines where we import $, and then turned on the scikit-learn multi-patch, which turns on anything that's optimized in scikit-learn. And that's all you had to do to see all of this performance gain. And again, all of these optimizations are available as part of the AI analytics toolkit. And the Census workload is actually available as part of the OneAPI AI kit code samples that I would be showing you later on what you could do to get started. So I've talked about a lot of these optimizations. The majority of them right now are currently on CPU, but where are we going? This is great for CPU, but I want more for all my other architectures. I want the same performance on all my other architectures. Well, this is part of Intel's much larger XPU cross-architecture programming model that we are aiming for. So imagine something such as NumPy, which is typically just on CPU, and being able to have data parallel Python and have data parallel NumPy available, not only on CPU, and be able to use that same NumPy API on GPU and other accelerations without having to change any of your frameworks, without having to worry about memory conflicts for like using too much memory for like different frameworks on different XPUs, different architectures. With the data parallel Python model, which we are aiming for, we are hoping to simplify the workload across all XPUs. So be able to use that same workload, not only on your CPU, but also on your GPU and so on, and using USM memory to help control the memory objects between all of these low-level frameworks so that say like the scikit-learn objects aren't creating extra objects just to work with XGBoost, ensuring that this is all under the hood and easy to use and controlled by our users. So this is something you could look forward to in the future as Intel looks toward this XPU programming model. So I will be going over, I see we have like around a 1 hour mark, but I'll be going over a preview into the deep learning workloads, which are the other part of AI Kit, which I didn't cover today. And then I'll be going over the demos and then Q&A at the end. But before that, because this was the main part that I wanted to cover, if you want to get started with AI Kit or any of the optimizations that I covered today, I highly, highly encourage you to download the OneAPI AI Kit. You could get it through Yum and apt install, offline or online installer. You could cont install specific optimizations. It's all free. Go ahead and do it. You saw the performance gain and how easy it is to use. I definitely encourage you to go ahead and use it. And if you don't want to download it on your own device, you could go to DevCloud and try these out on the DevCloud itself. We also have a bunch of forums that you could go to sometimes for specified parts, like OneDAL has its own specified forum. IDP has its own specified forum you could see here and ask your questions if you have any questions after this. You could also get this from one container, and then there's some AWS containers for some AI Kit optimization. So I'm going to pause and ask if there's any questions on that end-to-end workload I showed, or any questions on anything we just covered for the past hour. All right. Well then, since we have time, we are going to do a brief preview on the deep learning optimizations that are also available as part of the AI Kit. If you remember from the beginning, you saw that image. I'm not going to scroll all the way back to it of all of the stuff that's given as part of the AI Kit. And there was a part that I said we were going to ignore for right now, which is the deep learning optimizations, which include TensorFlow and PyTorch. Now we're going to go back and actually talk about those and what those actually include. So here are the Intel optimizations that run under the hood and Intel handles for you as part of these well-loved open source frameworks such as TensorFlow, PyTorch, and so on. Basically, through the OneDNN, library, similar to the one MKL library and one DAL libraries, which do those under the hood optimizations. We have the one DNN library for our deep learning framework. And what those do is essentially it helps you handle the scaling for load balancing, helps you utilize all your cores and improve the core utilization aspect of that. It improves the vectorization of these deep learning frameworks. And then it also improves the memory and cache usage, and then also provides optimizations to graph algorithms as part of this. Something I also want to do as a brief information, I specialize in all the classical ML frameworks and everything that we covered before this. So if you have any questions on these deep learning frameworks and the optimizations I'm going to go over briefly right now, I'll try to answer it, but I'll definitely encourage you, if I cannot answer it right now, to look at all the resources. We have a ton of resources on our deep learning frameworks. I definitely encourage you to look at those resources or ask in the proper forums for those questions. And I definitely encourage you to look at those if I cannot answer it. Again, my specialty is in classical ML and data analytics as we went into the past hour, but I want to give you this brief preview so you have a better understanding of everything you get as part of the AI kit and something you may be interested in beyond the classical ML and data preprocessing standpoint. So here's the breakdown. You can notice that this is a similar structure and diagram to what we had before in terms of, like, you could imagine, like, say this was like NumPy, you had one MKL underneath it, or for scikit-learn, you had one DAL underneath it. Similarly, we have a similar abstraction going on with TensorFlow, PyTorch, and Big DL. Underneath the hood of these Intel optimized libraries, we have one DNN running under the hood. And what it's doing is it's essentially, say, for example, it's essentially taking the memory intensive objects and unoptimized versions of the functions, and basically wherever it's unoptimized, plug in one DNN. For example, with TensorFlow, for memory, you usually have eigen running underneath. Instead of eigen, you have one DNN running underneath, and for the Intel optimizations for TensorFlow. And here is everything that is supported once you install the Intel optimizations for TensorFlow at PyTorch through one DNN. In terms of training and inference instruction sets, it supports float 32, bfloat 16 instruction sets. And then for inference, it supports float 32, bfloat 16, and float 16 and int8 instruction sets. And it basically helps optimize all of these functions that you see on the right. So for these compute intensive operations, such as like vanilla RNN, inner product, and so on, when DNN goes on underneath the hood to bring those optimizations, things that are memory bandwidth limited operations, one DNN helps fix those problems or improve those problems. And for data manipulation or reorder, one DNN helps with those as well. And you can see here on the left, what supports one DNN. So in terms of CPU, we have Intel Atom, Intel Core, Intel Xeon. For GPU, we have some Intel graphics, but I definitely encourage you to go onto the one DNN website or the AI Kit website for a better breakdown in terms of what supports all of these optimizations. And as we did before with all our other performance optimizations that we showed earlier, I want to show you what this performance actually looks like. So if we compare July 2017 stock non-optimized TensorFlow, which is considered our baseline, we compare that to Intel optimized TensorFlow in July 2017, the Skylake launch with one DNN, you can see a 50 times increase compared to the baseline. Now, if you fast forward to February 2019, compared to the baseline of July 2017, there's a 285 times increase compared to that July 2017 baseline. And in between, using Intel optimized TensorFlow from July 2017 to February 2019, you can see a 5.7 times increase just by simply updating your Intel optimized TensorFlow. As you can see on the right, with Skylake, we offer Intate instruction set, but with our Cascade Lake chips and beyond that, we actually offer another instruction set that's even better than Intate in terms of performance, called VNNI. You also hear it called DL Boost. But essentially for Cascade Lake and beyond, for those chips, if you converted your instruction set from Intate to VNNI, you could see at least a 2 times performance increase across these different models, which is again a great performance gain by simply changing your instruction set. And here is a better diagram compared to stock TensorFlow, and then the Intel optimized TensorFlow and its different instruction sets. So you could consider the blue, the stock TensorFlow, which is using FP32. And if we compare that to Intel optimized TensorFlow FP32, we see at least a 2 times performance increase in orange. And if we go even beyond that, and then we change our instruction set with Intel optimized TensorFlow to Intate, we see at least a 4 times performance increase. And with like ResNet 101, we see a 5.33 times performance increase. Now, if you converted your Intel optimized TensorFlow instruction set from Intate to VNNI, also known as DL Boost, you could see upwards, compared to that base stock TensorFlow with FP32, you could see upwards of a 7.87 times increase, or even up to 11.56 increase, depending on your deep learning model. Now, with these Intel optimizations for TensorFlow and PyTorch, what we also offer as part of the AI kit is Intel Model Zoo. So for your deep learning models, we want you to help achieve the best optimizations and best parallelism depending on your hardware and software and your workload. So with Model Zoo, what you can actually do is plug in your model to Model Zoo, and it'll actually provide recommendations to you based on like what are going to be the best parameters and configurations for your model using Intel optimized TensorFlow or PyTorch. And it will give you this breakdown in terms of what you should put for each parameter and what performance you could expect. So you also get this as part of AI Kit for deep learning. And these are the breakdowns for the configurations for what I showed you earlier in this. In this PowerPoint, I'm going to transition to demos, but if there's any high level questions for deep learning on what I covered just now, please feel free. And once again, everything I covered today is part of the Intel AI Analytics Toolkit. So any questions about anything?
Excuse me, ma'am.
Yeah?
I have one question.
Sure.
Okay, so for deep learning, I use TensorFlow, and I have NVIDIA GPU 1070. So I have TensorFlow GPU installed that takes the advantage of CUDA. So if I don't use GPU, then it shows something like TensorFlow can be optimized for AVX2 Intel thing. So am I getting on top of NVIDIA, am I getting this boost, or is it kind of a substitute for this GPU?
I believe it's, so I want to say right now, this is all for CPU optimization. So it's not running on top of NVIDIA. So this is for CPU optimizations for TensorFlow. So I don't think, I don't think it's running. Go ahead.
No, what I mean is, if I'm training my model on NVIDIA GPU, it doesn't necessarily mean that all of this computation is happening inside GPU. There are a lot of computations that happen in CPU and that are pushed to GPU. So if I install this, would this help me increase my speed or reduce the time?
So I don't want to give you a clear answer because just as I'm the subject matter expert for the other classical ML optimizations I covered, I am not as much the subject matter expert on these. I have a high level understanding of these. So I definitely encourage you to ask this question in either the AI Kit forum, or there's also a Intel optimized TensorFlow forum. And we have trained people who will help answer that question for you.
Okay, thank you.
No problem. I don't want to give you the wrong answer and then you see something different. Yeah. Any other questions? All right. So it's around an hour and 20 minutes in. So I think we have time for a couple demos. So what I'm going to do, simply move this over here. And we're going to go over some of the classical ML and data analytics optimizations I showed you early on in this. Now, a lot of these optimizations that you'll be seeing today, these are all part of the OneAPI AI Kit sample repo. So actually with OneAPI, what Intel has done is that we've put all of our samples across all the different toolkits into a single repo so that all of our users are able to get our examples in the same place, no matter the toolkit. And everything that I'm covering in terms of examples today are either inside the AI and analytics folder already on this repo, which is on GitHub. Let me actually copy paste this into the chat so you guys have an idea of this. And you can view this as well if you want to view this on your laptop. And inside this AI and analytics GitHub repo, we have 3 different folders. The first one being end-to-end workloads, which will show you, similar to what we showed before, a different combination of optimizations for different use cases. The Census workload with the performance gain that you saw earlier, you could see this in the Census folder. We also have getting started samples where if you just download AI Kit and you want to use any of these, we have these getting started code samples. And I'll be actually showing 1 or 2 of these today. And beyond that, we have features and functionality. So for things such as distributed linear regression or k-means with $pi, if you already learned a bit about $pi and you want to use it even more, you could look into this folder for features and functionality. And anything that I'm showing that is not in this folder today, it's either on its way to being in this folder or it's stored somewhere else within the Intel GitHub repositories. It's probably on the engineering project GitHub for this. But I'll be showing. But most of these samples you'll see are part of this example today. So with that, let's begin, and we're going to go in order. If I could find it, here we go. So this is our first example that we're going to go over, and I'm actually going to run it and then explain what's going on so we don't need to waste time waiting for this to run. And this is the getting started sample that I just showed you. That's part of the website. So, so in this example, what's essentially going on is that we're going to compare Modin to stock pandas in a single notebook. And we're also going to show you how to use Modin. And then as part of that, and then we're also going to show you kind of the coverage that Modin has, as well as the speed up you could get compared to stock pandas. So as with all data science workloads, we're going to begin by importing and organizing our data. Because we need a data of a certain size, simply to see like this huge speed up. With small data sets, you'll see a little bit of speed up with Modin, but it's really going to help you with these large data sets. So what we're going to do is actually use a synthetic data set for the sake of this sample. And we're then, after we're done with that, importing all our necessary packages, we're going to import stock pandas as pandas, and we're going to import Modin.pandas as PD, as you would normally use. After that, we are going to generate a synthetic data set using NumPy, and then we are going to save it to a CSV that we have called foo. This is just an example. After that, this is the step that is just frozen, so let's give it a moment. The workload is currently on this step, so maybe we'll see it in real time. But essentially, after we finished creating that data set, we're going to go ahead and read that data set first with stock pandas, then with Modin pandas, and they're both using that read CSV. And look, you could see the performance gain right here in real time with this magic time function. So you can see the wall time for just reading it with regular pandas, which is 47 seconds. But with the same, again, this is all on the same file, nothing different. That same file was read in about 1.92 seconds. And this is a pretty large file. I can't guarantee the size, but it's definitely over 1 megabyte, 10 megabytes, something like that. You could definitely go ahead and poke at it in your own time if you download this example. So let's go ahead and visualize what that looks like. And here's the performance gain. So Modin, you could see here, took around 2 seconds. And then here is the runtime for Pandas, which was much slower, as you could see within this visualization. Now we see that with read CSV, but what about all our other function? What about all the other function calls? Do we see similar performance with that? Yes. So as you can see with mean, which sometimes there's like a little, sometimes with these Pandas and like, you know, just in memory, if it doesn't run fast the first time, it runs fast every other time after that. So for data frame.mean, you could see that Modin was 1.52 times faster than stock Pandas. With apply map, Modin was 73 times faster than stock Pandas, huge. And then with concatenate, with Pandas concatenate, Modin was 7 times faster than stock Pandas. And beyond that, after that's done, all you could see, the rest of this sample is essentially showing you the coverage that Modin has for these Pandas functions, which essentially means that you could use other Pandas functions. It's, you know, it's not beneficial to do some of these functions and just have that performance gain throughout for every single function. You could do that on your own. But this is just basically to show you the coverage that Modin has with different Pandas functions. So you could use Pandas count, you could use filter function, iloc, so on and so forth. And once everything runs properly, and you'll see this in a lot of the code samples I'm showing today, if everything ran correctly, you'll see this code sample completed successfully at the end of this demo. So everything ran successfully, everything had speed up. So that's great to see. So that's the Modin speed up in real time. Again, usually you'll see the speed up usually on first try. If it doesn't work, it's like if there's like a very slow or like same speed up as Pandas, I definitely encourage you to just like run it one more time and you'll see that performance speed up. It's simply something at the memory level with caching, but Modin is definitely a lot faster than Pandas. I definitely encourage you to use that. Highly encourage you. And that's all in that single line of code change with Modin. Now, after that, I'm going to save this one for the end, simply because I'm going to have to break out of my Jupyter Notebook SSH tunnel that I'm currently in. I'm showing this. This is on an Intel lab machine that I'm showing it on. And I'm projecting the Jupyter Notebook to my local machine. So I'm going to save this distributed linear regression $Pi demo toward the end. But the next one that I'm going to show you is the XGBoost optimizations with $Pi predictions. So let's go ahead and run this. And let's go through what I just did. So because this is also a demo, and this is also based on a XGBoost Pi prediction example. That's part of the Pi GitHub. This is basically this is a .py file. I basically adopted this to a Jupyter Notebook and made it better to be explained. But all of these optimizations are part of AI Kit. So like we did with our first demo, we're going to begin by importing and organizing all our necessary data. And then after that, we're going to read CSV as part of the model. Again, this is just to show off the XGBoost and Pi prediction performance. So we're not going to use Modin here. All of these are isolated demos. So you'll see that each of these are only showing off a specific component. So what we're doing here is that we're reading in these synthetic data sets that were used as part of that original .py file this is adopted from. And we are going to go ahead and read CSV and get it ready for training. After that, we chose a couple of parameters to make this easier for XGBoost training. And then we're going to go ahead and train our XGBoost model using 100 rounds. Now, after that, after we've trained our model using the XGBoost API, I want to note, this is all using XGBoost API, this training. After that, we're going to use $pi for prediction. But beyond just using $pi for prediction, we're also going to use XGBoost prediction, but we're going to use it just simply for the sake of to compare the $pi prediction to XGBoost prediction performance time. So first what we're going to do, we finished training our XGBoost model. We're first going to predict using XGBoost prediction. As you can see here, I have like a kind of like simple timer that predicts before and after the XGBoost prediction using our XGBoost model. And then we're also going to just save that error count because we want to make sure that if we're using $pi prediction, we're not getting something different if we're using XGBoost prediction. So we're going to save the time and all that. And then next, we're actually going to go ahead and use $pi prediction. So we finished our XGBoost training model. Next, what we're going to do is take this model and convert it into something that $pi can read using this function called get_GPT model from XGBoost. And you just plug in your XGBoost model, nothing beyond that. After that, we're going to initialize our $pi object. We added a couple of algorithms just for the sake of this demo, a couple of parameters for the sake of this demo. And after that, we are going to time the prediction, the $pi prediction, using our converted XGBoost model that was converted for something that $pi can read. We're also going to save the accuracy for that after the timer is done and compare it. After that, we have this little assert statement, which is basically checking that the XGBoost and $pi predictions are the same. And since this didn't error out when I ran this in the beginning before I started going through this demo, you can see the accuracy is the same, but we'll visualize that in a moment. So we finished training our XGBoost model, and then we did two different predictions, one with $pi, one with XGBoost. Let's visualize it. So we finished this workload, and you could see here that all of the information that we're pulling, which is kind of just like the top of the predictions, like the first 10 predictions, and then the error counts and the accuracy scores. You see all this is the same. However, the only difference is that $pi prediction went much faster than XGBoost prediction, even on the small synthetic data set. And if we visualize that, we can see here that that $pi prediction using that XGBoost trained model had a 2.54 times performance speed up, and the accuracy is the exact same. So that kind of shows you the power that $pi has when you're using $pi prediction with XGBoost. Now, any questions with this or the previous demo I showed before I go into the scikit-learn demos, scikit-learn $pi demos? All right, I'm gonna take that as no questions. I have two more demos to show, and then there will be extended Q&A at the end as well. So let's get into those last two demos. The first one will be showing those scikit-learn accelerations and how you could actually turn them on. So I already went over the programmatic way in the presentation I did earlier. I went over the command line way. There's also a third way known as the environment variable method. And what this is essentially you take this environment variable, use $_pi_sklearn, and you just turn to yes. You could also turn to 1 or what have you, just something that means true. And once you do that, it will have the same effect as those 2 lines of code or using $pi in the command line, which is essentially turn on anything that is optimized by $pi. Turn on anything in scikit-learn that is optimized by $pi. After that, if that environment variable method isn't good and you want to double check that the monkey patch method works, you could use that just simply the programmatic way of just adding these 2 lines. I add these 2 lines to a very simple scikit-learn script that is available on the $pi documentation, I just basically copy and pasted this and added these 2 lines here. So what's going on is that this is just a simple scikit-learn script. I've changed nothing here. And all I've done is add these 2 lines, which like I've been saying for quite some time, all it's doing is adding anything that's optimized by scikit-learn from $PI, turn it on. So SCM is one of those optimizations. So that's what's going on here. So if I run it, here is what comes out. This isn't a performance demo, but you could tell that the optimizations are turned on because this little warning pops up, which says the $1 sklearn solvers are enabled. And it'll actually give you a link directly to the documentation if you want more information in terms of what is actually being optimized, as well as the rest of the $PI optimizations that are available. So there is that. I just kind of wanted to show you how easy it is to do that, as well as like what it'll look like when that actually runs. So you could believe that it's working properly. And with that, we are going to get into our final demo, which is this it? No, next tab. I have this little presenter tab that's making it a little bit hard. So our last demo will be showing you the distributed mode for $PI, and we're going to distribute linear regression training and prediction using $PI. I'm going to save this for later, because in order to use distributed mode, you actually have to execute this in a bash shell. I'm showing you this in a Jupyter notebook simply for the visualization. This is also available on the OneAPI samples. But for the sake of this demo, I'm just going to walk through this Jupyter notebook, and then I'm actually going to run this Jupyter notebook, which I saved to a .py file. I'm just going to run that .py file with this little command here, and I'll show you my bash script as I do that, or my command line as I do that. So this is just a little notice. Again, it's also in the OneAPI samples to tell you that this is just simply for visualization, but you have to run this in the command line. So for this distributed linear regression example with $PI, we are going to be predicting house prices in Boston based on the features of each house. This is a toy data set that is included as part of scikit-learn, and for the sake of this demo, it got multiplied 4 times. That's all that happened. Nothing different. It just basically got prepped for distributed mode by being duplicated 4 times and adding a little IP at the end of it. So like the rest of the demos we went over today, as well as data scientists workloads in general, we're going to begin by importing all the necessary data and packages. So we're going to be importing all of that, which is what we do here, import $PI. We don't really need this one. I'll delete this even. We're going to use train test split, pandas, numpy, and pickle to show off some of the features that we have here. After that, we're going to begin our actual workload. So the first thing that you're going to do is actually turn on the distribution engine for $PI through a single line, d for p dot $, and init. And what that basically says to $PI is like, I would like to use $PI distributed mode now. And once that initializes the engine using this line, you go ahead and read in your data, which should be prepped for distributed mode. And then we're going to just simply organize it for the sake of this workload. After that's done, it's time to train our model. We finished loading in our data. So we're going to train our data using linear regression. And you can see here that I've turned on the flag to true, which basically says, hey, fit this model with the independent data using distributed mode. So I want this on 4 cores, which is what we'll be doing, for example. And after that, what you can actually do is for each of these, so we're doing this on distributed mode, so we'll get 4 models. And what you can actually do is save these models somewhere. I'm saving this in the models directory, and you could save that somewhere. And if you want to use it somewhere else, like in a different workload, or to discern it, similar to what you can do with scikit-learn models, you can do so with pickle. So you can see here, we're actually putting our model into this .sav file, and we'll actually be loading it back up. So let's put this all together, since that seems like a lot at you. We basically trained all of our models. We've trained 4 models. Each of those 4 models are going to be saved to their own special model file that we could read or use anywhere else for whatever we want. We're going to take those 4 models that we saved and actually load them back up for our prediction. And here we've loaded our model, but we're actually going to show you one of the features. So say you want to use this model in a different workload, you could do so, or use just like the beta parameters. You could use that in a different workload. And that's basically what this is showing. This part is optional. These 2 cells are optional, but it's just simply to show you what you can do with $pi. So skipping that, again, we've trained 4 models with this train result. And then after that's done, we're going to go ahead and make a prediction for our Boston housing prices. So we're going to take the model from our training object, and we're going to take that and the test data, and we are going to predict. We are going to make a prediction. And again, this is happening on all 4 models. So you'll have 4 predictions, which will then come together and combine it. And once that's done with our prediction, what we can do is save our prediction to files. And then it's time to stop the distribution engine. And this will all, and you'll know that this happened. We're going to run this on 4 cores. And you'll know that this ran on 4 cores because this little code sample completed successfully print statement will show up 4 times. So let's go ahead and do that. We're going to train our model on 4 cores and then make 4 predictions and save them. And we'll see this 4 times, which will show us we did linear regression on 4 different cores. So let me, there we go. Actually, let me fix something first. I'm going to shut down the server for this Jupyter notebook. And it's fine. One moment as I get ready for this. I'm just basically going into my folders into the where the sample is stored. I'm just moving there. I basically saved the OneAPI GitHub onto my into this folder, so I'm just basically maneuvering to get to this. We are going to take this. It's going to be the file name. And then I'm going to move this over here. We're going to move that there. I'm going to zoom in so you can see. So this is a conda install that I did on I conda installed the AI kit. I actually conda installed the AI kit Modin environment, which includes IDP, scikit-learn, $pi, XGBoost, and Modin all together in that single install. So this is a separated, isolated environment for that. And essentially what I've done is I basically maneuvered within my all of these folders to get to the OneAPI GitHub and get to this linear regression folder to get to the sample. And then I'm actually going to run this sample within the folder. So I'm going to use MPI run -n4, which is going to note the 4 cores that we're going to run it on. And I'm going to run this Python file, which is just the Jupyter notebook I just showed you, but in a .py format. So let's go ahead and give it a moment. And it completed. So did it actually run on the 4 cores? You see all these print statements. You could delete these, but let's see that we ran linear regression just in distributed mode on 4 cores. So we'll see here. 1 code sample completed successfully. 2 code sample completed successfully. 3 and 4. And there you are. With the power of $pi, we have run optimized linear regression on 4 cores. And that is all the material I had prepared today. So are there any questions on anything with that? I'm gonna stop sharing. Actually, I'll keep sharing right now. Any questions at all? You could also reach out to Jeff or me. Let me put my email in the chat.
Yeah, I put my, this is Jeff Rogers. Rachel, great job. Thank you so much for doing another great job. I did put my email in the chat. Please feel free to reach out to me. Rachel has also provided her email now in there in the chat as well too, so that if you want to reach out to her, if it's anything outside of Intel Distribution for Python / AI Analytics Toolkit, please don't hesitate to reach out to me as well. So if you need information on any of our other tools, on 1MPI, on anything like that, don't hesitate to shoot me an email. I'll help you out. Make sure you got tools in your hands. In other words, get a license in your hands, and that you have any kind of support that you need on this as well too. But we certainly appreciate the opportunity to present today.
Yeah, if there's any other questions or information that you want, Jeff is a great resource on 1API and all of the great toolkits. But if you have any additional questions that you can't think of right now, feel free to ask in the AI Kit forums or to email me or Jeff, and we'll point you in the right direction if we can't answer it directly. All right, with that, I'm going to stop.
Thank you,
sharing.
Rachel. That was really quite informative. Very nice.
No problem.
Yeah, thank you guys very
being a
much for
great
doing
audience.
this.
No problem. All right. We have 15 minutes left, so I guess we could give that time back.
Thanks again for everything. Great job.
No problem. All right. Thank you, everyone. Have a wonderful day. Bye.
Thank you, everybody. Thank you for the opportunity. Take care.
So long, Jeff.